This video is going to be about rotational inertia. We've spoken about the word inertia before, and inertia is a lot like mass, but now we are talking about rotational, so we're going to figure out how does that concept of mass or inertia come into play with rotation. So as a review, we know that from Newton's second law, we know that F equals ma. And actually the way it's stated on the AP sheet is it says acceleration is force over mass. So we're going to use that as a starting point to think about, well, how does this relate to rotation? Well, in the rotational world, the equivalent, or the, not equivalent, but what kind of goes with force is torque. And this concept of mass, we are going to call that inertia. And then acceleration, well, we're still going to have acceleration. It's rotational acceleration, and so it's an alpha. And so if we rewrote this like it is with Newton's second law, we could say that rotational acceleration is equal to torque divided by inertia. And those two, that's how it is on the AP sheet. It's not F equals ma, it's A equals F over m. And the same thing with torque. It's not torque equals inertia times acceleration. It is acceleration equals torque over inertia. But in any case, if you can remember that F equals ma, and you can remember the equivalents that force and torque kind of go together, and mass and inertia kind of go together, then these should make some good sense to you. We also have an equation for the moment of inertia, which is sort of a numeric measure of an object's inertia. And the moment of inertia is the mass times the radius squared. And sometimes we do it as a sum. So inertia is the sum of the masses times the radius squared. And so when we talk about a moment of inertia, like I said a second ago, it's a quantitative measure of an object's resistance to changing its state of rotation. Sounds a little bit like momentum. Do you remember when we talked about momentum? And we even did a lab in class or an activity where we tried to stop the cart with our hands. And how difficult was it to stop that item, whether it's a cart or a ball or whatever? How difficult was it to stop it? That's the moment of inertia in rotation. So over in the margin here, I have written out the moment of inertia is basically asking how difficult is it to get a disc to start rolling or to stop rolling. And it doesn't have to be a disc, but when I think about these in the rotational, you might think about a big, heavy mechanical disc of some sort, and how difficult is it to get that thing started? And then once you get it started, how difficult is it to stop it? Another kind of comparison sometimes is like a bowling ball and a wiffle ball, let's say. So how difficult is it to get that ball rolling, and how difficult is it to stop that ball? And so that is the moment of inertia, a lot like momentum. All right, and then our SI unit for moment of inertia, all we are doing is we are taking the mass, that's kilograms, and we're taking the radius squared, so that's in meters. The radius is measured in meters. I'm going to put a little dot in there, so it's kilogram meter squared. That is the SI unit for the moment of inertia. This next section comes out of our textbook. It's table 8.1 out of the textbook, and it shows different objects. And each object actually has a different formula. You are not going to need to memorize these formulas, but you do need to understand the concepts. So we have this cylindrical shell, like a hoop, and it might have a variety of heights to it. That's not necessarily important because its inertia is mr squared, the radius squared times the mass. Okay, that is the moment of inertia. Now for a sphere, it's a slightly different formula. It's 2/5 mr squared. And if it's a solid cylinder, it's 1/2 mr squared. And if it's a spherical shell, it's hollow, then it's 2/3 mr squared. And these numbers, if you are in calculus, these numbers are basically becoming out of, you've got all of these different particles throughout. And so how are they distributed? And so that's where some of these numbers are coming from. We are not going to go into that, and we don't need to memorize that, but you do need to understand conceptually that different objects are going to have a different equation because of the way the mass is distributed. And however that mass is distributed is going to affect the moment of inertia. Let's take a look at these last two. Sometimes you can have a situation like this where it's not spinning along the axis like it was up here, like a disk. Instead, it's spinning that way, like an arm of some sort. And so that has even yet a different moment of inertia equation. And in fact, you can see that instead of an R, it's being replaced by L. And so similar deal over here. This one, the axis was through the middle, and this one, the axis is on the end of it, and so it has a different equation even still. And so let's look at all of these, and as you look at these, one thing that we want to be thinking about is if the mass is moved farther from the axis of rotation, how does the moment of inertia change? Well, how do you think that's going to change? If you spread it out farther, how is it going to change? Well, look at all these different formulas. And so as you look at all those formulas, the biggest one here is the hoop, or the thin cylindrical shell. That has the highest, right? All the others have a fraction of that. So this has the highest, so that must be the highest that's available. So as the mass is moved further away, it increases because that R is getting squared. As you change that R, if that R is increasing, that's going to increase the moment of inertia even more. By a square of it. So as the mass is moved further from the axis of rotation, the moment of inertia increases. The highest is the hoop, where all the mass is far away from the axis of rotation. And so remember, it's the R squared. That's, it's I equals mr squared. And so as things are going out farther and farther, it is increasing that R squared. The implications of this are that if you have different shapes that are spinning, then each is going to have a different moment of inertia. Each is going to be harder to stop or harder to start to rotate, depending on the shape. So that's something to consider, that the disk has the highest moment of inertia. Okay, let's turn the page. Okay, so this is just an example, a hypothetical example, but you could have something like this as a question. 3-point masses rotate about a common axis, as the drawing illustrates. Determine the total moment of inertia of the system. Well, that means we are going to come up with that summation equation. So the sum of all of the inertias altogether are each one, m1 r1 squared plus m2 r2 squared plus m3 r3 squared. And then if there were more of them, we would add all of them together. But again, in this case, we only have 3 of them, and so you would just plug in each of those numbers if the numbers were given to you and do it from there. And again, I think that if you are in a calculus class, you maybe could see how if you had a bunch of them and you were adding all those up together, how that would affect it. Question 15. I tried to put some objects in here that looked like what they're supposed to look like. So it says this is a thin-walled hoop and this is a solid disk. They have the same mass, the same radius, and the same axis of rotation. Which one would have the larger moment of inertia and why? So again, we're assuming that this is going to be the axis is through here. And if that were the case, which one would have the larger moment of inertia and why? Well, again, we talked about this a minute ago. The hoop is going to have the larger one because all the particles have a larger radius. They're farther from the axis of rotation. So all of these on the edge, their R is much greater. Whereas these, you're going to have to be adding up all the ones in between, and you've got some smaller ones, etc. But they do have the same mass, so it's the same amount of matter, the same mass, just distributed. All right, on this next one, we need to add in some dashed lines because it says the dashed line in each picture is the axis of rotation, and there's no dashed line. So we need to add in our dashed line. This one, let's say this one has an axis going this way, so it's spinning, going around it that way. Let's say this one has an axis of rotation down the middle, so it's kind of spinning around and around in that direction. And then let's say this one has the axis of rotation over here like this. Okay, and so the question is, which one is going to have the highest moment of inertia and which one's going to have the lowest moment of inertia? Take a minute to decide which one you think is going to be which. All right, let's see what you came up with. This first one should have the lowest inertia, moment of inertia, because it has the lowest radius. That means it's the easiest to get going and it's the easiest to stop. This one is going to be the medium because the radius is not as long as this one, but not as small as this one. And this one has the highest inertia, moment of inertia, because it has the farthest radius. You can see how long that's going to be, much longer than on either one of the other ones. So that it means that it is going to be the hardest to start and the hardest to stop. And sometimes it's easier to imagine one being harder to start, and sometimes it's easier to imagine one being harder to stop. Like for me, this one, if this is spinning around, depending on the speed of it, but anyway, if it's spinning around, are you going to want to put your hand out there and stop it? That's going to be difficult, right? Whereas this one, if it was spinning around, even if it was spinning around pretty quickly, I think you could see that it wouldn't take much to just put your finger out and stop it. And by the same token, this would be easy to spin. You could take just one pinky and spin this, right? Whereas this one, it's going to take a little bit more muscle to get that one going. So this has the highest moment of inertia. This one has the lowest moment of inertia. Sometimes we deal with these things called point masses. And so let's take a look at the problem. Determine the moment of inertia for the following situation. Assume the large solid disk to have a mass of 10 kilograms and a radius of 0.75 meters, and the small point mass of 0.2 kilograms to be located 0.5 meters from the axis of rotation. And so what's happening is, if you spin this around, this point mass is essentially going to be forming a hoop. But it's on top of the disk, but it's like the disk has one, and then this little hoop thing has another one. And so that's what's happening here. And so we want to know what is our total moment of inertia. And so we're going to need to set up and find out what our total moment of inertia is. And it's going to be the sum of the large one plus the small one. Well, again, as I said a second ago, this large one is a full disk, whereas the small one, as it rotates, it's essentially going to be causing a cylinder. Now, you do not have to memorize these formulas for the AP test. If there's something like this, they will give you the formulas, and they'll say, object A has a moment of inertia with this equation, and object B has a moment of inertia with this equation. And so you don't have to memorize them. So the large one it is a disk, and it has a formula of 1/2 mr squared. And the small one, because it's going to be creating a cylinder, has a moment of inertia. The equation is mr squared without a fraction, because it's just a cylinder, a hoop, basically. So now we just have to plug in our numbers and work this out. So I'm just going to take a minute to plug my numbers in here and work this out. Okay, so what's going on is we have a 10 kilogram cylinder with a radius of 0.75 meters. And then we have this little point mass, which has a mass of 0.2 kilograms, much, much smaller than the disk. And it has a radius of 0.5 meters because it was stated in the problem that that point mass is 0.5 meters away from the axis. So that's its radius. So all we need to do now is plug this into our calculator and see what we get as an answer. So why don't you go ahead and take a minute, pause the video here, and plug this into your calculator. Okay, when you plug that in, you should get 2.8125 plus 0.05. We add those together, and I'm going to call that 2.86, and it is kilogram meters squared. So remember that unit is kilogram meters squared. So again, this is just showing you that different objects have different formulas, but you don't have to memorize them. They would be given to you on the test. Okay, for the last problem, let's remember that we have the equation F equals ma, and that equation goes to torque is equal to inertia times acceleration. We also have another torque equation that we've learned before that is force times distance. In this last example, there is a mistake in the margin, so please cross off that last equation in the margin. That's a mistake, so I'm going to erase it, but it will appear later in the video, but please ignore that. Number 18, a uniform solid disk with a mass of 24.3 kilograms and a radius of 0.314 meters is free to rotate about a frictionless axle. Forces of 90 newtons and 125 newtons are applied to the disk. As the drawing illustrates, what is the net torque produced by the two forces and the angular acceleration of the disk? Okay, first question was about net torque, so let's talk about net torque. The net torque is going to be equal to, the net torque is if we have one force acting in one direction, which in this case would be clockwise, right? And we have another going in the other direction, which would be counterclockwise, then what we need to do is we need to find these different torques and subtract them. And that is going to give us our net torque. But like I said before, we also have that torque is equal to moment of inertia times acceleration. And so that's going to come and help us with our solving as well. But this is how we're going to set it up. So let's take a minute to set up our torques being force times distance. So we're basically going to take our force times distance going this way and our force times distance going this way. All right, well, our torques in the counterclockwise direction, we have the 90 times the 0.314. And then in the clockwise direction, we have 125 times 0.314. And so we can take a minute with our calculator and figure this out. And that's going to be our net torque. So that's question A. So go ahead, like I said before, pause the video here and use your calculator to see what you come up with. Okay, so we plug this in and we get that our net torque is negative 10.99 Newton meters. Negative because it is in the clockwise direction. So this is our net torque. So that's the answer to part A. Part B, though, asks us to find the angular acceleration. So that's why we needed this inertia times acceleration, because that's what we're trying to solve for. And so now we have a negative 10.99 Newton meters. And because we have a solid disk, that formula is 1/2 mr squared. And that, again, that would be given to you in the problem. Times the angular acceleration, and that's what we're looking for, the angular acceleration. And so now we need to plug in some information for our m and our r. The mass was 24.3 kilograms, the radius is 0.314, and then we want to square that because the equation is 1/2 mr squared. And so now we need to plug this into our calculator, and then obviously take the 10.99, divide by whatever we get here, and that will give us our angular acceleration. So take a second to do that in your calculator. Okay, so our angular acceleration is negative 9.17 radians per second squared. Why is it negative? Because it's clockwise. So we can see that the force is greater in the clockwise direction, which is obviously then going to give us a higher torque in the clockwise direction. And so therefore, our acceleration must also be in the clockwise direction. So the point of this problem, though, was just to kind of make sure that you can see all the different pieces of the equations you have to put together. That this torque was force times distance, so we had to use force times distance. But then we had to remember, well, torque is also inertia times acceleration. And so we had to use that 1/2 mr squared in the inertia to find the acceleration. So just an example of how a lot of times you have to know the equations, but you also mostly have to be able to pull them together to make sense of them. Okay, we will continue to work on some of these concepts in class tomorrow.